Today we are going to cover the chapter 7, the type system, and it is quite important because the data type and program type right now is leading the development of the programming language, and we will mention about this later. First, I would like to share with you for my course right here. This one is my course. Actually, I send this through email regarding this course. And this course is strongly related to our chapter 7 and 8. And I would like to have you to sign up for this course, but it is optional and it is free. So you should feel free to go in here. And also you are actually welcome if you have any suggestion on this. The reason why this course is quite important is for today's talk, actually, you should find out a lot of topic is related to this course. So that, and also the chapter 7, it only covers some theoretical backgrounds for this data type and type system. But this Java generic programming or parametric polymorphism actually will give you some real example for the topic we are talking about today. So please sign up this course, and it is free, and you will have lifetime access. You don't get blocked. So you can always come back for the reference. So now let's go back to our topic for today. Let's get started. Today we are going to talk about the type system, and in chapter 3 we already talking about name, scope, and the binding related stuff. That already related to data type and data binding and the computer compilers features of dealing with the variables. And in this chapter 7, we are not going to talk about the data types. Instead, we are going to talk about the type checking system mainly. How can the system check the type? And also we'll talk about the future development of the data types. So let's get started for the data types. Data type, we have the primitive data type, numeric, integer, floating point, character, boolean, and non-primitive, string, array, and the user-defined classes. So apparently this chart is defined by Java language. On the right-hand side, we have the general data types, and you can classify data as qualitative data type or categorical data type, categorical data. And on the other hand, you can also have the quantitative or numerical data. And this data actually is different from the data type we talk about in programming language. Actually, usually when you do programming, you are trying to collect the data from the outside world, and then you model it with your programming language. And they are quantitative and qualitative data. And quantitative data, you can have the numerical quantitative data, and could have discrete data and continuous data, or sometimes we call it digital data and the analog data. Even though this continuous still may be different from the analog data, but that is closer. And in fact, we have the discrete data space and the discrete or continuous time. So you can have the data of the discrete time and discrete value that we call it digital. And you can have the continuous time, and you have the discrete value. Then we call it discrete data, and sometimes we have the discrete signal processing. And sometimes you can also have digital data, discrete time, but continuous value. That actually is, some people call it, we'll call it like it's analog data, but in digital, in discrete time. Or sometimes you can call it like, if you quantize it into floating point value, you can call it continuous value. And there is also another domain that you have the continuous time and also continuous value, that usually is the real analog domain. So that's some data we would deal with from the natural world, and actually we use the Java language to model it. And data type, we all have developed an intuitive notion of what type are and what's behind the intuition. Collection of value from a domain. So actually you should have, say, weekday, you have the Monday, Tuesday, Wednesday. That is the domain. Internal structure of a bunch of data described down to the level of a small set of fundamental data. And this actually is talking about the primitive data type. And this set of primitive data type can be big, can be small. Some languages like Python actually have no primitive data type. It's all object type. And some language like C++ have a huge or much bigger primitive data type because C language is supposed to have all primitive data type and very few objects or none for C language. It only has the union or structure or record type. Collection of well-defined operation that can be applied to the object of that type. So this is somewhat like modularization or object-oriented program. Data type, purpose of data type, we can associate with a set of operations and semantic validity, higher readability. And I believe the first one, second one is easy. Higher readability is we want to specify a certain data type. So when you read the program, you can really understand what it represents. For example, we declare a class and we can have the class name as car. Then we know that this data is actually dealing with the car for the object. And for primitive data type, actually, with the integer or floating point number, you will know that we are dealing with some sort of continuous value, or we are dealing with the discrete value. Even though floating point number still be a discrete value, but conceptually, people would think about it as a continuous value, just lack of certain accuracy with the quantization error. So that is something that we define the data type, and we will be able to improve the readability of the program. And then performance optimization. If types are known at compile time, they can be used to drive important performance optimization. So this is done in the SSA stage and before the SSA stage. We talked about this before. Data type. What are types good for? Implicit context checking. Checking is very important. When you declare the data type, it's easier to check the data. But actually, this is arguable. Some programmers don't like to declare data type, but the system has to handle it, like in Python's case. And it has an advantage of not having any type for the programmer because it's so flexible, and you can be more like, you can deal more like in dealing with English, instead of feeling like I'm dealing with some machine language. But checking from the system or compiler point of view, with proper checking, it would actually bring in a lot of value. For example, you can prevent the meaningless operation and also can catch a lot of error at the compile time. So there are certain trade-off of how many data type we should have in the programming language and how much thing we need to do by the type checking system in our compiler. So polymorphism result when compiler find that it doesn't need to know certain things. So this actually data type has a few things. You want to make sure that your program is safe. You want to make sure that the user is actually program is actually easy to program, and then you want like have the polymorphism and also make the programming structure to support the kind of programming that you want to do and make the things easier and also make the whole system safer. Type system. So when we talk about a type system, it consists of the following two things. One is the mechanism to define type and associate them with certain language construct. That's type definition and the construction. So you need to have some way to build some data. Second, the type system includes a set of rules of type equivalence, type compatibility, and the type inference. And this is called type checking and type rules. And in this chapter, we are talking more about the number 2. And in chapter 3 and chapter 8, we talk about more of this definition and constructs. So in this chapter, we are more focused on the type equivalence, type compatibility, and type inference. This construct, variable object function, includes name, constant, variable regular fields, parameters, subroutines, literal constants, and expressions containing this. So actually, that is talking about the types systems. And let's go on. Rules. And this chapter, we focus more on type equivalence, type compatibility, and type inference. For type equivalence, it will be used to determine whether two values are of the same type or different. And this actually sometimes is whether we should treat them as the same structure or not. that is important, but compared to type equivalence, type compatibility is not even more important because it will determine the value of a given type can be used in a given context. So actually compatibility is more important because it determines whether certain parameter can be passed or can use a certain function or can be used to perform certain overriding function. So type compatibility is more important than type equivalence. We'll show this later. But actually, in this chapter, we show a lot of things actually focus on the type compatibility checking. And the third one is type inference. And type inference become more important in recent years because many languages like Python or JavaScript, these are very dominating language and very popular. And they dominate in a lot of website construction and also app development. And type inference actually is that you don't know about the type, but actually the system or interpreter can, based on the surrounding context, to determine your type. So actually that is becoming more important. And with proper type inference, you can actually hide a lot of technical detail from the programmer or user. In a language is polymorphic variable or parameter, it may be important to distinguish between the type of a reference or a pointer and the type of the object to which it refers. A given name may refer to objects of different type at different times. So actually that is related to polymorphism. We will talk about the importance of this later. Now let's look at the data types. The data type, we have strong typing and weak typing. And strong typing has become popular buzzword. So a lot of people like to have strong type language. It's like structured programming. Informally, it means that a language prevents you from applying an operation to data on which it is not appropriate. So you try to, a strong type language is like very strong definition of the data type. Say a student should do what student is allowed to do. So it's less exceptional case. For example, there's a data type for students, and then we try to make sure that there is no drinking alcohol option. Okay, that is one example I already gave. I can give, and actually, this is related to your programming language. Say we have a integer, and you try to say use the integer. For example, if your integer is trying to perform some operation that is not appropriate to it, for example, like that split, to split an integer, that's impossible because usually the split function is defined for only for string or some textual data. So those operations is not appropriate to a certain data type is forbidden, it's prevented. That we call the language strong typing. And some language with a lot of exceptions, we call it weak typing. Okay. And on the other hand, we have another thing called static typing. And static typing means strong type, and that the compiler can do all the checking the compiler. The first part, I believe, is not 100% suitable to imply strong typing. But the second one is what it really means. It is static typing actually means that you do all the checking at compile time, then we call it static typing. And if you check the typing at the wrong time, then we call it dynamic typing. So data type, we have, and here we're talking about dynamic typing to determine data type at runtime. The growing popularity of scripting language has led a number of prominent software developers to publicly question the value of static typing. So now the static typing is no longer the goal to pursue, and also there are certain debate on whether we should go for static typing or dynamic typing. And in fact, my understanding is it actually depends on the application environment. So it's hard to say which one is better. They ask, given that we can check everything at compile time, how much pain is it worth to check the things we can? As a general rule, it is easier to write type correct code than to prove that we have done so. And static typing required such proofs. The complexity of static typing increased correspondingly. So static typing actually add more efforts. Anyone who have written intensively in Ada or C++ on the one hand, and in Python scheme on the other, cannot help but be struck at how much easier it is to write code. So actually, here the argument is Python and scheme are much easier than Ada and C++. And I would say you cannot save anything if you don't do it at the programming time, or you don't save it, you don't do it at the compile time. You have to push it later at the runtime. So the execution is slower, but the programmer has the flexibility to do the things that they would need to do in an easier format. So there's a certain trade-off and it's hard to say actually. Dynamic typing to determine data type at runtime. Dynamic checking incurs some runtime overhead and may delay the discovery of bugs. But this is increasingly seen as insignificant in comparison to the potential increase in human productivity. And I believe that dynamic typing is becoming more popular, not because only for the human productivity, but also because the machine that we operate on is actually much faster, the memory size is much bigger, and the network is much faster. So dynamic checking is no longer a problem if there are certain runtime overhead occur. But of course, there are still some mission critical operations that you don't like to slow things down by adding extra efforts. The choice between static and dynamic typing promise to provide one of the most interesting language debates of the coming decade. So that is actually true right now. So right here show you the distribution of different language and its category. And on the right upper corner, we have Scala, Java, Haskell, C#, F#. This more functional language is actually more strong typed, more static type. So in this corner, as you can see, functional language, semi-functional language over here. These are all very strong type, static type. Okay. And on the other hand, this corner, we have dynamic checking, we have weak type. So it's script. All kind of script are falling in this corner. And something in between, you have strong type, programming, something in between programming language and script is right here. And some other language with legacy problem would be weak type, but static type. You check it at the compile time because all day you actually you don't have a lot of dynamic binding things, so you actually are in this corner with static typing, but weak type because this language actually have a lot of exception because they handle a lot of detailed situation for the machine related issues. So right here, as I told you, this 4 quadrant, you can think about more functional language, and here more script type language. And this corner, you have the regular language, but related to script. And this corner, you have the older language. And that's my rough idea about these 4 quadrants. Type system, common Lisp is strongly typed because it is a functional language, but not statically typed. I'm sorry, statically typed. And why is that? Because it's operating on list, and actually it's not really can be determined at the compile time. Ada, and in fact, common Lisp language has no idea of the type at all. It's actually in the very first version of Lisp, they don't allow to set value. So because functional language, it has no concept of memory. Even though later version, this setting of value as storage for variable is allowed, but the early version of this doesn't allow it. Ada is statically typed. Pascal is almost statically typed. Java is strong type with non-trivial mix of things that can be checked statically and the things that have to be checked dynamically. C has become more strong type, and with each new version, Actually, this C should be C/C double plus, because the new version means C double plus 11, and it's all combined. Though loopholes still remain, there are still some loopholes for C language because it's an old language. So the topic on this chapter will include meaning of the types, polymorphism, and orthogonality. And these three type checking things: type equivalence, type compatibility, type inference, generics. And in chapter 8, we'll talk about composite type. So in this chapter 7, as you can see, here are three type checking: polymorphism and generics. So that's why in the beginning, I talked about this generic programming course for you. And it's a short course. It only takes about 1 to 2 hours of the total video. And there are some program example as well. So you can take a look on it. And actually, that's why this chapter is strongly related to that topic. And I make such a course for you guys for free. So right here, let's look at the generic programming. And I would like to use this example to conclude our first part for this chapter. Is I'll give you some idea of how the programming language goes. So let's start with the C language. C language is beyond assembly. So it actually has a structured programming with a lot of procedures. So in C program, you actually see a lot of function call. You have a lot of function. You have pointer. You have structure. You have union. So everything is structured in C language, but that's not enough. And then later we have the module. We have the object-oriented programming, and we add this into C double plus, and C double plus also include generic, or actually you call it as a template. At the later version, succeeding C, we have this added. And the purpose of this is to add the object-oriented programming. We basically add three concepts: encapsulation, inheritance, polymorphism, and this one coming with dynamic binding. And polymorphism actually also allow the classification of objects. And also with generic, actually you are able to copy the template for different object classes. And that actually add one more layer to C language. So the key idea of generic programming or programming with template is to define family of function and classes. So for example, we have a stack, and that stack is operating on stack of integers, stack of double value, stack of strings. Then these are considered as the same family of classes. They are all stacks of different value, but actually they can share with one template, and that template can cover all the classes. That is the advantage of generic programming over the object-oriented programming. So generic programming is to make the object-oriented programming even simpler, and it is actually included in C double plus as template, and it is included in Java as generic programming. And that's not even enough. So later people start to think about functional programming. And functional programming is when functions, not object or procedures, are used as the fundamental building block of a program. So we need to have first class functions, higher order functions, natural closures, pattern matching, single assignment. Okay, this single assignment, I mentioned it in compiler. It should be chapter 4 when we talk about the static single assignment. SSA in the compiler stage of optimization. I talk about SSA actually is functional programming, and it show up here. I'll explain this later. And actually, daily evaluate, because it evaluate late. Garbage collection, that will clean up the environment. Type inference. Type inference is given the function, it should be able to operate on different object type, and actually it hide the data type by just doing inference. So from this part, you will see the difference between generic programming and the type inference. In generic programming, you still need to define the data type, but in functional programming, we give a certain function, and that function should be able to operate on the data type without knowing about the function, without knowing about the data type. So functional programming from this point of view is another extension of the generic programming. So objects actually build up classes of different data type. And these data type actually give you the idea of what's inside the object. And then generic programming will group different object of the different classes into certain template, or we call it generics classes. And we group that into a certain template. So we don't need to repeat the definition or programming of different classes. And that is extension from object-oriented programming. And functional programming do one more things that actually is hiding the template. So actually, when you apply some function on it, type inference will be applied. So you don't need to know about what object or what template of objects we are actually working on. So that is the type inference. With type inference, we can use the function for recursive. So we have the tail code optimization to optimize it. We will be able to perform everything with proper function. So we call it a first class function. So whatever can be put in certain place can be done. That's the orthogonality that we talk about. And then we can operate on higher order functions to make it faster. And we have the closure. We have pattern matching that's related to type inference. And we have the single assignment. So in the detailed implementation of the functional programming, we actually assign a certain name for a certain assignment to optimize the performance and something like this. These are the nature of the features of the functional programming. So right here, actually, there's another chart. Generic programming is actually expanding object-oriented programming, and it also and object-oriented programming is on top of object-related programming. And actually, this one is like a modularization. And then we have imperative programming, that's like C language that has no idea of module and the objects. And actually, functional programming is interesting. It actually can be on top of the imperative programming. For example, like using C++ or C# on top of C language, that's one layer. And the relationship between the generic programming and functional programming actually is not that clear. Some people say generic programming is bigger than functional programming. Some people say the other way, because these two fields are still growing. So the boundary and the definition will vary from person to person. So the main idea of having the functional programming is we get the input to a certain function, we get output. So right there's no storage, and we just pass value on. And that's different from Newman's finite state machine type operation that has storage. So right now, there is a big, and that storage we call it mutability. And actually, that's the main battle right now between the traditional monument model and the functional programming. So let's look at the future language. Who's more functional? Groovy, Kotlin, Scala, or Java. These four languages are all on top of Java virtual machine. So in fact, they don't have that much difference. They all on top of Java virtual machine. So right here, as you can see, recursion all supported, and then ADT abstract data typing also supported. And I think ADT is one of the important features for functional programming. And pure, nothing is pure right now. And okay. And these four languages are actually coming up. Java 9 will be ready on July, so it's coming soon. And this Groovy have been there for a while. Kotlin is catching up. Scala is dominating. So let's look at the distribution of their popularity. I'm sorry, so right here. Let me check. I have one page. Sorry, I missed one page. Actually, I made a mistake on here. Okay, one moment, please. What happened is that I usually have this weekly presentation folder. I should create a shortcut paste, but actually this time actually I physically copied it, so I do not get into the right version. So let's close this one, and actually let's delete this local copy. Keep this shortcut. Okay. You know, this is called coherence problem. When you have multiple copy, they should be the same copy, but they don't, then you will have trouble. So that is the coherence model we talk about in chapter 5. So right here, show you the next Java virtual machine language to learn. And all of these are on top of Java virtual machine. And as you can see, Clojure is 12%. And then Kotlin is only 2%. Scala is 47%. Groovy is 31%. So if you want to pick one of the language, I would say I will pick Scala. And in fact, many of you actually pick the Scala as the topic for your term project. That is a good idea if you want to focus on knowing about the next Java virtual machine language or future functional programming language. Even though this language may be good, and the reason why I would suggest to pick either this one or this one is because that usually programming language you need to go for the majority, and that is another factor you would choose because they may not have all the features that the other guy has, but in the long run they will improve. And because if they are popular, and they will actually absorb whatever good nature they have and become more popular. And if you are the underdog, it's hard to turn back unless you have the potential to have to get some destructive feature that nobody can catch up. Otherwise, the leading guys usually will continue to lead. But between these two, I would say they still no clear winner on here. So pick one of these would be a good idea. But of course, the term project, you are not limited to these two languages. You can learn any language that you never learned before. I originally has a limitation of not using the C family language, but if you do pick C, C++, I would now I would say, probably say, won't say no to you, because I know that very few of you actually have the C plus background. So if you really think that that's a language that you would like to learn, it's not bad to learn at all, actually, because they will still be there for a long time, and they will continue to serve a lot of applications. And by the way, this chart is from this Rebel Labs. Now let me check if my system still recording. Okay. Because there's a week that we missed the recording. Excuse me for water. Now let's look at the G2 data type. And every language you will see such domain value, wrapper type, primitive type for the data types. So it's denotational data type is denotational, structural, and abstraction-based view. We will talk about this different view later. And actually, right here for primitive data type, a few things are important. Is the size, how many bit or bytes it occupies, and also how many how is the value. In fact, here the Boolean is set 1 bit. In real implementation of the C language, I'm not sure it's actually 1 bit only, so you have to check. And in fact, C language is a data type. The size and the primitive type offered will vary from installation to installation. So in C language, there is no uniform way of the data type. Some installation may have long double, and some installation don't. So it's hard to say. And right here, actually, this one is a range for wrapper type for Java, actually. But every language will have such a table. So here is the domain. Type definition, a type system. We have discrete type and scalar type. Discrete type means only one data field. So you have integer, Boolean, character, enumeration, subrange. All these are countable, means they are certain. They are just certain discrete type. They are just 1, 2, 3, 4, or anything that is enumerable. And everything in this type, discrete type, will have limited elements. And the other one is the scalar type. You have discrete and real. For real value, actually, you can have the floating point numbers. So it's different from a discrete data type. So discrete data type is one part of the scalar type. Scalar means one dimension. So right here, show you the enumeration type. In Pascal, it's defined as type, weekend, and such. In C language, C double plus language, it actually starting from the C language, it's only using this define. It's actually, you can also look at this as a macro. So let's just replace the top left as 1. So this is the early day how people use enum in C language. And later in C double plus, we have such definition. I'm sorry, in C language later we have such definition. They start to have the enum, and then later in C double plus, it got taken over by C double plus, and in C double plus 2011 version, it not only has such definition, but also it start to allow the type definition. So that's the advances in C++11. And right here, show you C, C++, and C#, right here, and Ada, and Java. Java's case is different from the C, C++. Java has a special class called enum, and actually you can put the initial value or the constant value over here, and actually it comes with certain function as well. So actually that's the enum. Enum in Java is more like a class. It's a specialized class. And C, C++ or C++11 is more like a type definition or more like a record. It's more like a type definition, I'm sorry. And then here is the subrange. Subrange actually have different meaning in different language. Let's look at the Python's case. We can have a list like this, and you can use the subrange for the index. So if I have the column 5, it means like starting from index 0, ending at 5, but not including 5. So you get 0, 1, 2, 3, 4, up to here. That's your subrange. And then right here, in Python's case, if you have a range 20, that means that starting from 0 to 20, and then you make a list and save it to an array, and then you actually use that to get some range. Right here, you set this range 3 to 7 to this value. Actually, you will assign this value to these different ranges. And there's a range function for Python. You have the start, stop, or step. And if you have 3 tuple, you will have start value, stop value for the value, and then step as the step size. But if you have only 2 tuple, that would be start and stop. So if the step is omitted, the default step is 1, and then you have the range starting from 0 to 7, but define a sequence of this 0, 1, 2, 3, 4, 5, 6. And if you have the 0 and ending in -1, that means, I'm sorry, if you have 4 starting from 4 and ending in -1, but not including -1, actually it will be 4, 3, 2, 1, 0. And in this case, the step size is actually -1. So it really depends on the direction you move up or move down for the step size. Okay, that's about the subrange. Subrange actually in Pascal is defining from 0 to 100. It's actually a range, and workday from Monday to Friday, but you need to define a certain enumeration before you can use this subrange. Now let's look at this type definition for pointer, ages, and references. So we have a that's a variable. We store 3 in there, and then we have pointer, PTR. So body of this, actually this @ sign, we call it ages of or @. Sometimes I pronounce it as @. And this one actually is overloaded with the ensign in bitwise ensign in C language, but somehow this make the C language not a strong type. So actually this, I call it as @, but somehow it's actually mixed up with the operator with the ensign, bitwise ensign in C language. And this star, I call it as content of, object of, or body of. Usually I call it body of because content of an object of sometimes will create confusion. So I call it body of. So right here you have a pointer PTR. The body of it is a integer. Then I can assign the ages of A, that's the ages of A 2001, to PTR. So PTR will be storing the ages of A. Then the body of PTR will be the value 3, because the pointer is pointing, its value is storing 2001, so it actually pointing to this object. That's value 3. And then we store the edges of PTR to PPTR as a pointer to a pointer. So we store the edges of this to here, and then we finish. So let's show you the chart of this table, or this program, sorry. So this one we call it variable, this one call it a pointer, and this one we call it pointer of pointer. And up here we call it ages. And single star we can call it the object of or content of if it shows on the right hand side. Type, pointer to function. Right here is the way to declare a pointer or function. So right here we declare a f pointer, function pointer. Body of the fptr is a integer type function with 2 integer parameters. That's what this pointer is. In fact, this declaration only declares a pointer of 4 bytes in the memory. So you won't have the function body. So it just stores certain ages of a certain function. So if we have a function A, we make such assignment, then the ages of this function A will be stored at the fptr, or this function's pointer. So the function name actually is a function pointer. It actually pointing to a certain function body. So the function body's ages is this function names variable that assigned to fptr. So fptr execution with the 2 parameter, this will be sent to the parameter list of the function A. And actually this one is executing function A. So we call this a pointer to function, that the body of a pointer is an integer, and that integer is an ages. And that actually complete, this one actually complete the function call. Same for this. So XML language has such big built-in data type because XML is supposed to be a important language for resource management. So it has very complicated data type, and it's more like a scripting language. So it actually allows a lot of different data type. Type system, composite types. We have record, structure, variant, records, or sometimes in C language called union, array, string, sets, dictionary, or sometimes in Java we call map, pointer, L value, and this actually is the reference type. List and file. So these are different composite data type. We will mention it in next session or chapter 8. And here show you the difference between structure and union. A structure is to a record. So this structure employee type, E type. This name, this is the variable name. So right here, it actually store 1 character, X, for 1 byte, and the 114 point number of 4 bytes. And in this case, if you use the union instead of structure in C language, it actually X and Y actually sharing the same memory location. So the largest one of the two will be the size of this union. So this one floating point is bigger, that's 4 byte. So actually the size is 4 byte. But at one time, there's only one data over here, and you can interpret it, the union in different way. So it allocates storage will be equivalent, it will be equal to the largest one. And union is used for memory sharing. But this different composite data type, we will actually talk about it in chapter 8. That's the next session. Let me check how much slides we have finished. We are on 29, about 30, and we have about 96 to go. So we are at the 1/3 point, about 1/3 right now. And we are about 40, 50 minutes right now. Okay, pointer and reference. Here are different bases for comparison. So we had the comparison, the basics, and return value, the operator. And let's look at this operator. So if you have the star sign, that's the pointer body, and this dash arrow sign, I call it the pointing the value. So a pointers with this dash arrow will go to its body. So you can think about it as a go-to. So the pointer go to its body. That's the referred data type. And the body's address will be equivalent to a pointer. So this S sign actually is overloaded too much actually. And I will actually omit the different things. We will focus on these two. So reference type is string array object in Java. Pointer is its L value, left side value. So it's address actually. Now let's look at the type system number 2, the polymorphism and the orthogonality. Polymorphism, we talk about this many times. You have 4 types of different polymorphism. And for generic programming, it actually is related to subtype polymorphism and parametric polymorphism. And we won't repeat this too much. So basically, let's go to the more examples. So in Java case, we have this type, I should say that this is a type parameter as item. So here, actually in definition, you have a type variable. And this type variable can be assigned with different type arguments or type variable or type parameters. So this declare this class is a template of different classes with different generic type. And it will allow this different method to operate on this item type. And item can be different objects. That if you assign certain type parameter over here. So actually this is a reactive buffer, but this buffer actually can buffer different type of objects or data. And it has the is empty or add something to this buffer or get something from this buffer. So this is one of the data collection type buffer. And in C language, you actually, this is implement of a generic swap function. To use a generic swap, to define a generic data type, in C language, you don't have the object type, so you actually use void type. So void type actually will be, now this one is body of X is void. So actually X is a pointer to a void data type. But since void is not a data type, so you just declare a 4-byte pointer. And this 4-byte pointer, when you assign certain, say, integer type or floating point type, it will always be okay because void is compatible with them. So that's related to type compatibility in C language. But at least this void in C language is working like object type in Java. So now we accept 2 pointer in here, and then the body of this X actually the body of this is X is assigned to temp, and then temp and Y assigned to X body, and then temp assigned to this Y body. So right here you have a character type, and the type passed in, you actually is casting the pointer type to a pointer of integer. You cast it and find its body. So right here you have two operations. First one is casting the pointer type from void pointer type to integer pointer type, and then that pointer type finding its body and assign its body to temp. And right here is similar. You actually convert a void pointer type to floating point pointer type, and so this X is pointing to a pointer if the character type is defined as a floating point, and that floating point data will be assigned to ftemp. So this one actually complete the swap function for an integer data type and a floating point data type. And if the type is not defined as these two types, and then we will call it illegal data type. So this one is the C's way to handle generic swap. And pretty much, if we look into Java, sorry. If we look at the Java's case, if you think about the implementation, pretty much it will be similar to the C case. So C will be too detailed, but it actually show you the implementation. And subtype polymorphism will show up in C++, and also alpha, I misspelled it, and then OCaml, Java, and C#. So this is the polymorphism in Java with the subtype polymorphism. So object type in Java is used like the void type in C. So this object type, since it's a higher class in the object tree, so it actually is compatible with any of its subtype. So any object type will be compatible with this. So this one actually, if it is not operating on certain class defined operations, then every object type can be used for this method. So we actually trying to add an element to a certain vectors. So you basically get that object and clone it and then put it into a pair. And that pair is actually a vector. So this one is the subtype polymorphism in Java, one of the example. And right here is dynamic type language with support for unified polymorphism. So this language actually Ruby, Python, Smalltalk, and Objective-C. Python and Ruby is Ruby is a descendant language for Python, so this is in one family. And Smalltalk is the first and very pure object-oriented programming language. So these three actually has a very strong support for polymorphism because of their nature for object-oriented programming. So they have a unified polymorphism. They accept dynamic typing, inheritance, multiple inheritance. And these two actually is not for Java, and the rest of it all supported. So here are the nature of the unified polymorphism, what is needed for polymorphism. Type orthogonality. Orthogonality is a useful goal in design of a language, particularly in this type system. A collection of features is orthogonal if there is no restriction on the way in which features can be combined. So basically, orthogonality, we talked about this before. Whatever it is, it should be allowed in wherever it is defined. That means if I say this is a variable, and then that language structure should be able to apply to anywhere there is the variable is accepted. That's the orthogonality we need to implement. So for example, Pascal is more orthogonal than Fortran because it's more structured, because it allows array of anything, for instance, but it does not permit variant records as arbitrary field of another records. That is actually still one exception. C or 16 has no distinction between statement and the expression. Orthogonality is a nice orthogonality is nice primarily because it makes a language easy to understand, easy to use, and easy to reason about. So let's look at the next thing. The void type is is used for just to void type. It should be allowed to. So the casting actually don't care where it went. So here we have one function, and it actually assigned to full index. And this same function can be casted to void. So cast is optional, implied if omitted. So right here, Pascal, it has no void type, then it actually use dummy. So this same symbol table, we can assign this, declare this as a symbol table index to dummy variable. That's variable type because there is no type definition. And then we actually can assign these functions return to dummy type. So dummy actually is just like void type. We don't know what the return value is, but since we use dummy, but that dummy is available and it can accept whatever this function returns. That's the way that Pascal is handling the casting and also handling the polymorphism and subtype polymorphism. In fact, in Pascal, there is no subtype, the concept of subtype, but it's actually acting like that. For Java, the corresponding object will be cleaned by object collection for any pointer assigned with null value. And that language, if you assign null to a value, it won't clean it up because she, in some implementation, has a object collection. And in general, if you want to free some memory, you need to run free or some memory allocation function in order to do that. For enumerations, we add an extra none of above alternative to the set of possible value. For these two techniques are very different, and they don't generalize to types that already make use of all available bit patterns in underlying implementation. So basically, to erase a certain value of a certain variable, as long as the language is consistent by itself, there is no clear definition of what it should be for different languages. And for functional language, provides a special constructor called option or maybe. These are the language that with the special constructor for erase of value of variables or the null values. And now let's look at this OCaml's case. And it actually is n divided by d, 2 parameters, and return value is 14 point. So with d, you should match the d, and this parenthesis star is actually command in OCaml, so you can ignore it. So the option is actually matching d with 0 or anything else. For 0, you should return none. For underline, you should return some, and then you actually return the value of n divided by d, and then we match this v, the whatever return value it is. If none, then we print out this question mark. If some x, then we return this x as string of 14 point. So this show actually will be showing the value of this division in the string format. Orthogonality, erase the value of variable. This one is optional. And this is the strict way to write the previous example. Orthogonality aggregates. The aggregate assigned to P and A are positional. Let's look at this. Ada has a record of name and age, and name is 10 character string. And actually right here, P is a person, Sorry, this one has a typo. It should be lowercase. And in fact, it's because usually Microsoft PowerPoint would convert your lowercase later, leading lowercase later into uppercase. I should actually modify this later. And then we assign this one is for the name and 37 for the age. This is called positional assignment. And for P and for Q actually has the double arrow sign. This double arrow sign actually will assign 36 to age. So this is B is not positional, but you use the double sign to assign the value or to the argument, the value to the record data fields. So this is how Q and B are assigned. And A is actually 10 integer, A is 10 string. A is actually integer, so it's actually 10 integer assigned to A. And B actually has this double arrow sign to assign 1 to first integer element, and then assign 3 to 3 element with array element with index 3, 5, or 7 that assign with 3. Others you assign 0. So that's the way Ada allow aggregate initialization. So it's actually like a initialization by spatial structure. Now we will start to talk about type equivalence. Let me check if there are anyone. Okay. We'll start to talk about a type checking system. Type checking, we have three different things to check. First, type equivalence. When the two types of value are the same or different type. Type compatibility, when can value of type A be used in a context that expects B. So whether a certain data type is compatible or not. Third one is the type inference. What is the type of expression given the type of operand? So actually it's from the operand to infer what type of the data type on the expression, on the expressions variables. Type checking, here we talk about type compatibility and type equivalence. Two are very similar, but slightly different. Compatibility is more useful concept because it can tell you what you can do. Because if two types are equivalent, they will be default compatible. So usually, if you have the type equivalence, it already is compatible, and then this checking is actually not that important. So usually we are checking in the more redux format of the type compatibility, but type compatibility provide more useful concept. So the terms are often used interchangeably, but actually they are not the same. Let's look at it. Right here, if you write this way, these two are the same. And if you check this, these two are actually also the same. So basically the type equivalence is like, you should think about if after compilation, the data storage is the same, you can actually call it as type, these two types are equivalent. So type equivalence, two major approaches, structural equivalence and name equivalence. The first thing is called name equivalence. Name equivalence is based on a declaration, lexical occurrence of definitions. Structural equivalence based on some notion of meaning behind those declarations, but can equate types. Programmer doesn't intend to consider lower levels. Name equivalence is more fashionable these days. So usually people just use the variable name to determine whether they are equivalent or not. And in Java, C#, Pascal, Ada, they are all using name equivalence. And in structural language, for structural equivalence, these are all the structural language, Argo 60, A, Modula 3, ML, and C. Name equivalence, variant alias type, semantically equivalent alias type, semantically distinct alias type, and the derived type and subtype. So here we'll have different definition based on different alias. The difference between all these approaches boil down to where you draw the line between important and unimportant difference between type description. So basically, even name equivalence, you can have alias type, semantically equivalent alias type, semantically distinct alias type, and derived type and subtype. So here, actually, still have different way of defining name equivalence. In all three schemes described in the book, we begin by putting every type description in a standard form that take care of obviously unimportant distinction like those above. So let's look at the variant, the first type, alias type. We have a type, new type equals old type, and type definition, old type, new type. These are actually trying to make one type equivalent to the other type. This is the OGO's family language. Type definition, old type with new type, that's for C language. So right here, if we define unsigned integer 16-bit type for mode type. So this mode type actually is defined as unsigned 16-bit integer, and this mode type is for permission, user group, and then user read, user write, and user group. So this actually is some of the file access permission word. So this actually is the RWX type, similar to those kind of the permission word, but it actually stores as 16-bit unsigned integer. But these two, if it defined like this, the two actually can be used interchangeably. So this is called semantically equivalent alias type by type definition. Another one is called semantic distinct alias type. And these two are declared both in, I believe this is actually, it should be ADA. And then actually both are declared as real type. So if you declare this with these two different types, even though both of them are declared as a real type, but these two are actually not compatible, and this is called semantically distinct alias type, and this is not allowed. So alias type is okay to use interchangeably because for the type definition, semantically equivalent alias type, you can assign a value interchangeably, and semantic distinct alias type, the two are actually not compatible. So unfortunately, there are other times when alias type should not be the same. Ada allows such loose name equivalence, but this will be prohibited. Type checking, structural equivalence depends on simple comparison of type description, substitute out all names. It spans all the way to built-in types. Original type are equivalent if the expanded type description are the same. So this actually it actually show you like talk about to use the structural equivalence. So it actually will depend on the final compilation result to check the comparison. So here are the type conversion and the casting. Let me check. Okay, so structural equivalence actually only depend on the comparison of the dictionary. I was just I would actually omit the structural equivalence right here because not a lot of language actually implement this. So let's talk about type conversion and casting. These are more important. So because most of the time we are dealing with the casting to convert from one type to the other. Number 5 show you the implicit casting of the data type in Java. So actually, basically, shorter can convert to a longer one or wider range one, but not vice versa. From double to character, that you need to have the explicit casting, and from primitive data type to reference data type in Java. Sorry. You will have boxing and auto unboxing from byte to byte. This part is wrapper class, and this side is the primitive data type. You have the boxing and auto unboxing conversion. Sorry. And then right here, we have same type for left-hand side and the right-hand side. We have A equals some expression. If the same type, then you can directly do the assignment. If you have on the right-hand side, you have different values. Say we have integer, we have float, or we have sometimes even string for Java's case, but not for C's case. We can actually do automatic conversion on the right-hand side with the implicit rules. And that would be assigned to the left-hand side with the more general data type. So the plus sign is overloaded. It can be plus operation for integer floating point number. It can also be a concatenation for string, but this is only good for Java or C#. Automatic conversion for the parameter. Parameter will also do type compatibility checking. And actually, this casting is actually implicit for compatibility checking. So that's the automatic conversion for the parameter. So a few locations that would happen. One of the automatic conversion is in assignment. The other one is right-hand side automatic conversion. Another one is a parameter matching and conversion. And we also have the explicit casting way. Type conversion in Ada. In Ada language, the type would be structural equivalent, but the language use name equivalent. The type have different set of value, but the intersecting value are represented in the same way. The type have different low-level representation, but we can nonetheless define some sort of correspondence among their values. So actually right here, let's look at the example. It's easier to understand. N is an integer, R is a real number, T is a test score, so it actually should be also an integer, and C is Celsius temperature. So this is another integer or floating point that I believe. So actually we can convert the N integer to test scores type to T. And then we can convert T to integer back to N type. So these two actually are, I believe, are equivalent. If you look at the structural equivalence, they are equivalent, but both they are okay to convert back and forth. And you can convert N to R from integer to real. Actually require runtime conversion. And then convert R to N, but also require runtime conversion checking whether it's compatible or not. Sometimes you will lose some value. From C is Celsius. If it is integer, so there is no runtime call required. Same thing from N to C. Non-converting typecasting is called typhoon. Conversion that doesn't change the bit. N bit to N bit conversion. So right here, if we cast, occasionally the system program will need to change the type of value without changing the underlying implementation. One common example occurs in memory allocation algorithm, which use large array of bytes to represent heap. So if you have, say, convert from integer to floating point, most of them are, say, 32-bit. Then in Ada language, it allows you to convert from integer to floating point or floating point to integer without checking the semantical meaning. So that's called unchecked conversion. That's a built-in generic non-converting casting. So Ada allows you to do non-converting casting, but some language don't have this feature. This non-converting typecasting is called typhoon. Back now we are on the type compatibility. Before we go through this type compatibility, I'd like to have some review for the type equivalence. So as you can see, that type equivalence part for this textbook, it actually is not very clear what is going on. And in fact, that topic is very bizarre, and also different language have different way of handling it. And most of the modern language just allow the name equivalence. So actually, if the two variable or two object of different name, they pretty much are considered a different things. So those type equivalence issue is only bothering some people who use C language or older language. Those people will be bothered. For modern language, type equivalence shouldn't be any problem at all, because all of the modern language just implement the name compatibility. So name equivalence. So we have such a discussion, but actually it is not that essential. Let's get started for this type compatibility. This one is more important. Type compatibility, most languages do not require the equivalence of type in every context. So that's what it is. It's not so important. They merely say that a value's type must be compatible with the context in which it appears, where it can be used. In an assignment statement, the type of right-hand side must be compatible with that of the left-hand side. As long as the right-hand side can be converted or coerced to the type of the left-hand side. So any casting or any combination of the data fields that can provide the right value for left-hand side, that would be a acceptable case for most of the modern language. Same thing for parameter and the operands matching. Type coercion, whenever a language allows a value of one type to be used in a context that expects another, the language implementation must perform an automatic implicit conversion to the expected type, and the implicit conversion will depend on the implicit conversion rule. Type conversion. We have type conversion and type coercion, and usually type coercion, the word is used in the implicit conversion or implicit casting. Now we call it type coercion. Coercion has the meaning of forcing something into different type. So it is actually an implicit type conversion. So in C language, you can convert implicitly from integer to unsigned integer to long to unsigned long integer, something like that, to long double. Long double is the longest one. But not every C implementation has a long double. And the disadvantage of coercion decreases types error detection ability of the compiler. In most language, widening conversion of numeric type in expression can be coerced. So making the data from more limited data, more limited field to a wider definition domain will be allowed, but not from the wider to narrower. In ADA, there are virtually no correlation in expressions. Because of the ADA's nature of no correlation, so some people say that it's safer. So ADA actually is usually used for defense or military use or something that demand higher security. When an expression of one type is used in a context where different types is expected, one normally gets a type error. But what about this? If we declare A as integer, B, C as real, and then A plus B equals C, this is actually allowed because many languages allow things like this happen, and coerce an expression to be of the proper type. Coercion can be based just on type of operands and or can take into account expected type from surrounding context as well. So actually you can judge from surrounding data to determine certain variables type by implicitly conversion it. Fortune has a lot of coercion, all based on the operand type. Type checking, C has a lot of coercion, but with simpler rule. C all float in expression will become doubles. So actually C is forcing all of the floating point to doubles. Short integer and character will become integer. So actually this is similar in Java. If you do plus sign, and all short of character will be converted to integer. If necessary, precision is removed when assigned to left-hand side. Recent thought is that this is probably a bad idea. So actually, some people say this is not good. But for me, I think it's still a good idea. And in fact, personally, I would say only using int and double is a good way to define a language. We don't really need that many data types actually. Ada allow little conversion, implicit down conversion. Fortune Pascal has little more rules, and it doesn't matter that much anymore. C double plus Perl go hog wild with coercion. They are one of the hardest part of the language to understand. So some language can make the coercion really hard to understand. Coercion in C. So right here, show you the example of coercion in C. And it's actually making C as weak type language. So we have integer S, we have unsigned long integer L, we have character C and F, floating point F and double D. Okay, and then these two are in IEEE format. So then we have this long integer assigning to S that's short. So because this one is longer, this one is shorter, so lower order bits will be interpreted as unsigned integer. But this one show integer actually is signed. So you only assign a lower bit. So for example, like short has 16 bit and only 15 of the unsigned bit. So this long integer is unsigned, so you only assign about 15 bit into S. And then from S to long, you will do sign extension. But after the sign extension, actually, The long integer is actually unsigned, so it should be interpreted as unsigned long integer. So, for example, if this s is -1, and -1 is actually 1111 all ones in two's complement. So this L will be a huge positive value of all ones because it's unsigned. And then from C, that is a character assigned to show integer, that will be from one signed character to one signed integer. Show integer 60-bit, this is 8-bit. So actually you would perform sign extension on it. From long integer to floating point number, you will put this into Mantissa and adjust the number of bits accordingly based on the single precision, but some data may be lost. And then from F to D, this one is from a narrower definition to longer definition, so it's okay. You will be converted without losing data. But D to F will lose the precision, but it will not create dynamic semantic error. Techniques used in conversions in C language. So here show you how to do the sign extension. For example, we have one byte that is actually a character data type, and it's actually signed character of F0. F is 1111, 0 is 0000. Then if we assign to unsigned integer, we actually will do 0 extension. You can also call it 0 extension as sign extension because it's actually extending the sign bit. So, and then if you assign to sign integer, you will extend the bits. I'm sorry, the top one, 0 extension is doing it on purpose for unsigned integer. So actually it's extending the 0 to observe that it's a positive integer using 0 extension. And right here is lost bit and the lower bit sign. Here is the format for character short and long. And from long to double or long to float, it may lose precision but wider the domain because your 64-bit integer need to convert it to 52-bit fractional part in double format or only 23-bit part. Actually, it will lose some bit information, so it will lose precision, but expand the domain. Conversion in Ada, we have such enumeration type. So D is a number, but it's enumeration type. K is an integer also, and it is also in enumeration type. And then C is a calendar type, and it's also a weekday type. So weekday type, actually you have from 1 to 5. Workday probably that's different anyway. So from D to K conversion is different types, so you need to do runtime checking. From K to D, actually the workday. So workday should be the working day, so it's only 1 to 5. Weekday probably is also 1 to 5. So actually this one is no checking. Maybe workday is a weekday, so actually it's okay. And for D assigned to C, D is actually workday, C is a calendar column. Calendar column is actually longer, 7 days, so we'll create static semantic error. Overloading and coercion, we have noted that we have noted that overloading and coercion can sometimes be used to similar effect. So this process actually is overloaded, but because of this overloading, we actually will need to coerce on the operators either with addition or for concatenation so that different data format can operate together. So coercion can still allow process to take integer argument, but they would always be converted to real if there is certain real in the expression. In some language like Java, if one of the operand is string type or characters type, numbers will be converted to string due to the overloading of the plus sign for concatenation. So right here, show you a big example. Say we have the sum of plus A plus and plus B plus is plus sum, such a long statement. Usually you have a system that print out the print line parentheses with this. Or you can assign this whole thing to a string. So we get started from the sum of plus 8. You will convert from 10 to a string. So two strings concatenate together. And then we have the plus sign and then end. It will further be concatenated to this string. And then we will have the plus b, and b is 20 will be concatenated together and continue. And at the end, we build up a long string. If either operand of plus sign is string, then the plus operator becomes string concatenation. That's how it works. And if it is not string, but it is a different number, then we need to depend. We will find a wider number format to use. Universal container type. This one is the void pointer can be a pointer to any type, but it can only be used after it is committed to a certain real edges. And in different language, we have different universal container type. Include we have any. In Module 2, we use edges. Module 3, we use euphony. And Java, we use capital object. C# we use the lowercase object. C double plus use void star. So right here, the pointer PTR is declared as a void pointer. And then these three have different edges. But since this one is a universal container type, so anybody's else pointer edges value can be assigned to the same pointer. So that's how this polymorphic, I'm sorry, not polymorphic, the so-called the universal edges type, pointer type, is used in C language. And then it can be used to create a generic function. As we see the swap function before, using the void pointer to allow the generic computation in C language. Java container or object. So object, when an object is removed from a container, it must be assigned to a variable of appropriate class before anything interesting can be done with it. In a language without type tag, the assignment of a universal reference into an object of specific reference type cannot be checked because objects are not self-descriptive. There is no way to identify their type at runtime. The programmer must therefore resort to an unchecked type conversion. And these are the rules for the object. And right here, this example, we create a new stack to my stack, and then we have as such string, and we new function new for new object new full, that's user defined class full, and then we push s and f into my stack. And my stack is actually generic type because there is no type specification. I'm sorry, it's not generated, it's row type. So actually it pushed these two data into there. But when we retrieve the data, when we pop out something, it returns a reference value to the string, but actually you need to cast it back to string. Otherwise, the data stored in the stack is actually of object type. And this actually is the old way of handling the object and generic type in Java. A new way we have the type variable and generic construct. So if you want to know about the detail, again, you need to look at my video for it on the generic programming. Type inference. Type inference, what determines the type of overall expression, type checking for the output. The result of an arithmetic operators usually have the same type as the operands. The result of comparison is usually Boolean. The result of a function call has the type declared in the function's header. The result of an assignment has the same type as the left-hand side. So here we have different basic rule for type inference about the arithmetic operator, the function call, the Boolean, and the assignment. In a few cases, however, the answer is not so obvious. In particular, operations on show subrange and on composite object do not necessarily preserve the type of operand. Type inference permit modern language. So modern language, all like JavaScript, they all allow the type permission. So right here, they all allow the type inference. So let's look at this example for type inference. Type inference is a function which automatically specifies the type that can perform inference if not the necessary minimum type is specified, like in the figure. If this function is used, the advantage where error can be checked at the early stage can be realized without specifying the type of all the variable and functions. So right here we have a variable, but this variable actually we don't know about the type, and we pass it to integer argument 1. Then number 2, you go back to determine what type it is. So this is called a type inference. And this is the use of the function, and this is the declaration statement of a function. So basically you pass the parameter in, and then you return. Actually, you just matching this argument. And there are several ways to do type inference. So right here, let's look at the type propagation. For type propagation, we have function foo xy that will return the x plus y, but we don't know about the type for x and y. Type bar, the same thing. It will return foo of b and a. Actually, this one, they reverse the order. So we have declared a variable quark with bar and this hello and goodbye. But this quark, actually, we don't know about the type because we just declared it as available in in JavaScript. So we pass these two values in a string, and this actually is a bar function. We pass these two value to function of bar, and that actually is a bar function call, but in reverse the order, and then pass to the call of the full function, and then actually b go to x and a go to y, and then the two plus together. At this time we know this is string, so string, these two are string, these are string, and here are string. So two strings sum together still a string, pass back to the return value. So the return value will be a string of two concatenation, and then pass back to the return value for the bar, still string, and then at the end, it pass back to the call of the bar function, and then it returns the correct. So you can see the function type as orange box containing reference of abstract value. Function declaration will cause such a subtype to be created and added to the variables that names the function. The purple box are propagation strategy. There are two calls in the function corresponding to the two purple boxes, call boxes. At the top is a simple box that handles the plus operator. If a string is propagated to it, it will output the string type. And if two numbers are received, it will output a number type. So this is called type propagation, and type propagation is used to finish the type inference. I'm sorry. And type inference actually, if here you don't declare it in some language, it's just based on the value that you pass through to here, it will actually be able to determine the type and then return to it. Just like this type propagation. But type propagation is one way of determining the type of the return value, but it's not actually the only way. So declare type in C++ 11, C++ 11 with declare type keyword that can be used to match the type of any existing expression. The type declaration keyword is particularly handy in templates. So right here, where sometimes it's possible to provide appropriate static type. So we have a template accepting two types. These two types are actually for generic. So we don't know until the runtime. And then, I'm sorry, we don't know about the type until you compile it for the template. So this A type and B type used to declare these two objects. And then we declare type of A plus B for this sum variable. So the type declare type is used to declare a new type, but this new type is based on the expression A plus B. So this is actually one variable, but in fact, this declare type will calculate the type of this sum based on A plus B. So if A, B here are string, then it would actually be a string type. But if it is integer and double, then it will become a double. And if it's two integer, maybe this one will become an integer type. So this is how the declare type keyword will be used. So with this feature, the generics in C++ 11 actually not only be able to complete whatever that can be done in Java, but it actually perform more operation actually on the type definition, and actually it is more flexible in this way compared to Java. It can actually do calculation of type. Type taking in ML. ML is actually a whole family of language, and it actually is an old language for ML, but nowadays nobody is actually using ML. But the most sophisticated form of type inference occur in the ML family of functional language. It includes Haskell, F#, and the OCaml and SML dialect of ML itself. Programmer have the option of declaring the type of object in this language, in which case the compiler behaves much like that of statically typed language. But we know that actually functional language, a lot of them are more like dynamic binding, dynamic type language. It's more functional. Okay, programmer have the option of declaring the type object in this language, in which case the compiler behave much like that of static typed language. So usually it's a dynamic type language for these different functional language. But functional language actually it all depend on what type of functional language it's about. If it is well defined like Scala, it is very statically typed. And this rule-based language is more dynamic type, but it still usually is a strong type. So these actually more will be put more on the left top corner of the quadrant for strong type and static type. Programmer may choose not to specify type, then compiler have to infer them. The key inference mechanism is to unify the type information available for two expressions, whether the rule of the distance says that their type must be the same. So type inference mechanism usually is used on the information on the expression. So it actually will still be similar to such calculation or the pattern matching. So the basic idea for type checking are actually not far different. Any discovered inconsistency are identified as static semantic error. Any expression whose type remain incomplete, please specify after inference is automatic polymorphic. So this is the implicit parametric polymorphism. So type checking, to be sure, type checking is one sort of the implicit parametric polymorphism, and this happens a lot in functional programming, and actually is a implicit and actually automatic polymorphism. Let's look at the slides I showed before. That's how we, in the very beginning, I'm talking about type inference is a feature for functional programming. And in fact, it is also a feature for generic programming. And in fact, the relationship of the generic programming and functional programming is not that clear cut. So you don't know whether functional programming is bigger than generic programming or generic programming bigger than functional programming. It all depends on who is talking about this topic or depend on the individual's idea. So in C++ case, functional programming is actually bigger than generic programming. But in Java's case, Java moved up to generic, and actually it has the Scala or something like expanding it. But in Java alone, you actually look more like generic is covering the functional. So it all depends. So in ML's typing, is static typed, type checking the compile time, is strong typed, the mixing of the can be done explicitly, and inferred runtime. So actually, ML language is more functional, and it actually is this language actually fall into Haskell is on this corner, F# in this corner. So it's all in this corner, more static. But some of the language in this functional programming language, actually they have dynamic binding, not dynamic type, dynamic binding feature. So actually this chart is somewhat okay, but you still need to talk about the dynamic typing and the dynamic binding. It can be static typed language, but it can also be dynamic bound language. So this idea actually is quite different. Static typed means that the type inference is done in compile time. But when you allocate the parameter or object or some data storage, actually it's done dynamically. So it can be static type, but dynamically bound language. So that's what you need to be careful about this ML family functional programming language. So basically, inferred type is running long-time pattern matching. Even though type inferred, basic type still have this. ML created by Miller and to specify utilize the HM type inference algorithm to automatically invert the type of expression. So they have their own inference mechanism. Type inference, the ability of a programming language to automatically detect the data type of a variable. A compiler is often able to infer the type of variable without explicit type annotation having been given. Why is it useful? A programmer does not have to explicitly define type annotation while still maintaining about the same level of type safetyness. Type often clutters program and slow down programming efficiency. So actually, type inference can improve the type productivity, but may slow down the execution speed. But it is actually default for this ML language. But in newer language like Scala, it also considered as a Java virtual machine language, but it also has a functional feature, so that become much more popular right now. ML inference. So right here we have a function f of x equals 2 plus x. Of course, we don't know about the x the data type. So how it works? The plus sign has two types. The plus sign has the integer times integer go to integer, or real times real go to real. So integer has only one type. So this star should be considered as an operator. And for this plus sign, we actually has the integer plus integer go to integer. So from the context, we need an x of integer type. So that's what it is. And here, this one is the inference rule. So therefore, f of integer has a type of integer. I'm sorry. But if this x is a real number, you will use this real plus real. You will go to real. So right here, we have OCaml language. Is one of the ML language families. Successful example. It has a tail recursion Fibonacci function. So that's f Fibonacci n, and Fibonacci n is the basic Fibonacci. The helper function is right here. It is recursive helper, Fibonacci helper. So it has n1 and n2 and I. This n1, n2, and I will code the following things. It will return the helper list. So if n equals I equals n, then we will return n2. Else, we will call the helper n2 mapping to n1, n1 plus n2 mapping to n2, and I plus 1 in helper 0, 1, 0. That's the initial condition. I'm sorry, that's the termination condition for this. The inner dots in construct introduce a nested scope. The function Fibonacci is nested inside Fib. The body of the outer function Fib is the expression of this. So when you call this function, actually you are calling this. So this is the starting condition. I'm sorry, I tell you wrong. This is so initially you will pass this to call this Fibonacci, this, and once you pass in, if n is not equal n, then you will call this. If equals n, then you will return n2. That is the termination condition. So you start from smaller n2 to larger n2 until it is n. So from 1 calling to n2. The body of this, it will evaluate either n2 of the Fibonacci this, depending on whether the two argument of Fib is n or not. So basically, initially you had the 0 and 1. So basically, it's n1 and n2 are storing the Fibonacci number of n and n minus 1. So initially you put 0 and 1 in, and then after then you call 1 and 0 plus 1 as the Fibonacci number of the F2, and then F2 pass to here and here. You have the 1 and 2, then 2 F2 pass here, Fibonacci 1 plus Fibonacci 2 will become Fibonacci 3 that will pass the code here. So I keep track of the number n, and this n plus n1 plus n2 assigned to n2, this keep track of the is the current Fibonacci number, and this one will be the Fibonacci number minus 1. So that's how this tail recursive Fibonacci function works. But the thing is, like, you still need to match the data format for this data type for this OCaml function. So parameter I has the type integer. It keeps track of the number n the current level that's calculating, and eventually it will go to n. Parameter n must be integer type, and the call Fib helper, it will have two type of the n1 and n2 of integer. The type of I is consistent with the earlier inference. The type of the argument to the recursive call at line 4 are similarly consistent. Since Fibonacci helper return n2 at the line 3, the result of the call in line 5 will also be integer. Since Fibonacci immediately return the result as its own value, the return type of Fib is integer. Okay, this is how they determine the determine the types. Let's take a look at the next slides. So initially, because this 1 is an integer, I plus 1 continue to be an integer, and then you determine I should be an integer. So I is an integer, so n is an integer. N is an integer, so initially you actually call n is an integer. So you push in the I is an integer, and then you will return the n1, n2. So these two are all initially integer. So they pass through here. So n1, n2 are all integers. And then n1 and 2 are integer. One I is also integer. And then this helper function will return integer because it will return n2. So Fibonacci I, n1, n2 are all integer type. So that's the way that type inference Sorry. That's how this whole thing is talking about, how the types are determined. Other type checking in ML, checking with implicit type, you actually can specify the input type and the output type for a function. That's also possible. And expression type inconsistent. For example, you can write this as this. If the circumference to apply the circum to integer, it will create inconsistency. And type variable a and a to bool. This means two arguments of the same type to produce a result of the Boolean type. And big quote a is a type variable. So this actually is a type variable in ML language. Right here, we actually cannot represent this back arrow because on keyboard, it actually will create such type of the code. So I'm sorry on this typing. Type checking, all occurrence of the same identifier have the same type. In an if then else state expression, the condition is of type bool or Boolean type. So this condition is Boolean type for sure. And then and else clauses have the same type. A programmer defined function has such a type variable where these are the type variable for the function's parameter, and R is the return type. The last one. The last one is the return type, and these two are the parameters type variable. When a function is called, the type of the argument that are passed are the same as the type of the parameter in the function's definition. The type of the application is the same with the result of the function's definition. First, let's talk about the parametric polymorphism. It's also called generics. In some language, there are implicit parametric polymorphism, so you don't need to do anything. They are born in the language. The ML family languages are naturally polymorphic. So right here, as you can see, this is a minima function for OCaml. And you actually provide two input parameters, and that will return, this function will return the minima value of the two. So if x less than y, then return x. Otherwise, you return y. In OCaml, our mean function would be said to have the type quote a go to, or quote a go to, and the quote a. This one actually should be the same sign as this, but the problem is when I use the Microsoft PowerPoint, it actually will automatically convert it to the second quote. So that's what is going on. But anyway, these first two are the type variable or type parameter for the first two, x and y. And this last one will be the type variable for this return value, y or x. In Haskell, it would be audio a go to, a go to, a go to, and a, something like this. So this is left-hand side. You use the double arrow sign. While the explicit parameter or mean are x and y, we can think of a as extra implicit parameter. So actually, this is implicit. ML family language provide implicit parametric polymorphism. Parametric polymorphism, implicit parametric polymorphism. This is actually in Ruby, and actually Ruby is similar to Python, as I mentioned before. So this mean actually is a minimum function applied to this list. So you will return 3. And this one come in with a range, and with for mean that will give you the minimum value for the value in the mean. And this one again is a list, and it's using the alphanumerical order or alpha lexicographic order, and A pole will be the lowest one. And the last one, it uses minimum, but it redefine the compare operator. And in Ruby, mean function is a predefined method supported by collection classes. The element of the collection C supports a comparison, so we actually use C.mean. This this is called compare operator, will be returning the minimum element. So actually, this one will be comparing these two values, get the minimum value of it. For the last call to mean, there is a trading block. Alternative definition of comparator operator, so the operator being redefined. The operational style of checking is called duck typing. What is duck typing? Is if it works like a duck and quack like a duck, then it must be a duck. So if it look like an integer and it behave like an integer, it should be an integer. That's the rule that we are talking about for the duck typing. So duck typing is actually often used even in the programming language. We have strong typing, weak typing, and another thing is this duck typing. Duck typing means if it look like an integer, it should be an integer, something like that. Generic subroutine and module, polymorphic method and polymorphic classes. These require the explicit definition for the generic functions. Generic module or classes are particularly valuable for creating containers. So usually generic module are used for collections of data structures. Generic subroutines are needed in generic modules and may also useful in their own right. So either you use the method as a library method, so it can be called by many people. That actually is, say, for example, like a sorting or searching algorithm, that it is useful by their own. And it can also be a generic function in a generic module. So generic, you have three types of different generic things: generic function, generic data structure, or generic container, and a generic parameter. Generic function, that is generic mean, generic maximum, generic sort. Language provide generics including Ada, C++, LFL, Java, C#, and Scala. Generic data structure usually is like queue, stack, vector, and list, those type of things, and generic binary tree. So containers including queue, stack, heap, set, dictionary, or map abstraction implemented as list, array, tree, or table. Generic parameter supporting compile time and customization, allowing the compiler to create an appropriate version of the parameterized subroutine or course or class. In Java, C#, generic parameter must always be types, and actually it's normally true. So it can be used as a variable or function of data structure. So right here, show you two versions, one non-generic version, one generic version. On the left is non-generic version. So basically, you need to write one version for integer, one version for long floating point value. But actually, most of the code are duplicated if you just look at the begin and end. And right here, it shows you the generic declaration. It comes with one generic parameter and one generic function and return value. This parameter is actually type parameter or type variable. So right here you have a return type of Boolean, and then you have XY of the type T, something like that. So actually you input Chou value for comparison, and return a Boolean value. So right here, you can actually, the first one is the type variable, that's T. And then next one is the comparator. So basically, you have these two are matching here, this one and this one. So it's integer and less than. So basically, this is the integer min function. You can use eta with the function in min is new min this. So this is actually one template. You use that to create an integer minimum function, real minimum function, string minimum function, and date minimum function. C double plus generic container. C double plus is using the template statement, but your class need to be following the template in order to get the effect for generic definition. And right here we have two things declared in the template parameter list. The first one is a class. This class actually is the item type, that's generic type, and it is actually shown in here. This is the generic type item. And right here we have the pointer for actually a reference value or address value for item. Here we have a pointer value for it. These are of the type. So this item is just like T in Java. It actually is a generic type. And then next number has a default value of 100, but it's an integer type. So you can actually put in any number you wish. Right here, so you have call this 2 times, call Q 2 times. The first one, you actually pass in a type variable process. So ready list is actually a queue of process. And process we put in here, and its maximum time is 50 in this case. So actually, this will be creating a template, a class of queue class of the process type for a ready list, and also create a queue of integer type for 50 elements, and both use these same templates. Now we are going into the part 2 for implementation, and this is the last lecture in this chapter. So right here are the comparison for the mechanism for parametric polymorphism. So ML and this are implicit polymorphism, that's for sure, because both of them are functional language. But one thing to understand is the actually the type checking issue. This using the dynamic typing, and ML use the static typing, but providing the type inference. But actually this one is quite robust. And on the left-hand side is explicit definition of a generic, and actually C# and Java subroutine instantiation is implicit. Implementation option in C double plus or ADA, you use a separate copy. So you have a template, but those templates are used to actually create different copy of the code so that you won't mix up. So guarantee all instances of a given generic will share the same code at runtime. That's for Java, but C double plus ADA would use a separate copy with proper data structure, because C double plus and C actually their call frame or local variable actually need to be predetermined. So for each function's call in the memory, actually the size are different. So they probably is using the separate copy would be a better idea. But Java actually you have a dynamic linking. So your library, if it is built as a generic, then it need to be used for every people they call you, because they will access you at the runtime. So Java has an object type. In principle, all objects share some polymorphic method, which are member functions
or member method of object class or direct inheritor of object class. So actually, this using the object type is one way that you can guarantee that at the runtime, you don't need to determine the size of the object because it doesn't show up in the call frame and it shows up in the heap. So this type of generic operation won't be harmful to Java. Create a special implementation of generic code. This is how C# is handling it. So right here, we have a generic parameter constraints. So in Ada, we can declare one T type that is generic data type, T array type that's a generic container for integer of certain range, and another is a functional comparator. So all of these are different generic type. Without the with statement, with clause, procedure so would be unable to compare element of A. So basically, you need to define this comparison function. It supports only assignment, testing for inequality and equality, and a few other standard attributes. So you can see actually this is one of the attributes they compare. Generic parameter constraint. So leave right here, it is the Java version of the same sorting algorithm. Let's compare this and the Ada case. In Ada case, you have to declare this T and also T array and the comparator. But right here, actually, because of Java's interface, so it actually can use the comparator T and is expanding this comparator interface of T type. So it actually it stands as a T itself is actually a comparable class, and comparable class will have the compare to function. But remember, this one is a lowercase. Again, it's a typo error. So, any comparable function, the class will have compare to function, and compare to function will allow it to be compatible with the standard arrays, the sort, or this sort algorithm. Right here is the C# way of implementing it. Similar to Java, it has a type available over here. But here we have the definition of this T that is extending interface comparable. So actually, this is similar to Java's case, has a T stands comparable T. These two are similar. And in C++, we have to use the template type name to define the array type and also the size. And here is implicit instantiation. By certain matching, you actually will instantiate the type and type variables and comparators. And right here, you pass through these two into the templates items and maximum item variable. Okay, generics in C++, Java, and C#. Excuse me. Sorry. Generic in C++, Java, and C#. Several of the key trade-offs in the design of generic can be illustrated by comparing the feature of C++, Java, and C#. So C++ is the most ambitious because it provides a template, and template you can write everything you want to be more customizable. And Java and C# provide generic purely for the sake of polymorphism. So Java and C#'s generic is more like under the object-oriented programming. It's a part of object-oriented programming, so it's smaller. And C++ one is actually more ambitious, so it actually support more like functional programming type. And Java's design was heavily influenced by the desire for backward compatibility. So right here, I have two courses to help you. The first one is the paid course. I do not recommend it, but the second one actually is one I send out for email in the email, and you can take a look at this course. It will help you to understand the generics. And that's it. Thank you. Bye-bye.